Hi folks, welcome back to Physics with Captain Rod. I'm making this video to provide an example of solving a second order homogeneous differential equation, including initial conditions. So what we're looking at here's our equation that we're going to work with, d squared y dx squared plus 3 times y equals 0. The idea here is we're looking for the function y as a function of x that satisfies this equation, as well as the initial conditions written over here on the right. That in addition to solving this, we need that y of 0 to be equal to -2 and y prime at 0 to equal 0. All right, well, let's begin here. So for starters, all right, because of the plus sign here, we believe we're going to see trig functions that solve this. So a sine function may solve it, or a cosine function may solve it. In general, either. And what's called the general solution is the sum of the two. So I'm going to start with a general solution that I believe probably looks like this. Y equals a sine bx plus c cosine dx, where a, b, c, and d are constants to be determined later. Now, there's really just three things we can do here. One, sub into our equation. Two, apply initial conditions for y. And three, apply initial conditions for y prime. That's really all we can do here. And I'm going to go ahead and apply some of the conditions first, starting with this one. When you see a 0 condition, that's usually a good place to start. So I'm going to use the condition that y prime of 0 needs to be 0 before I even mess around with this equation here, and see if that will yield me any useful information. So if I take this equation and we differentiate it, this is going to read y prime equals a, b, cosine bx, right? Because the derivative of sine of bx is cosine bx times b. This term is going to be minus cd sine of dx, and that's because, pardon me, the derivative of cosine dx is minus sine of dx times d. Now I'm going to go ahead and apply this condition. This needs to be 0 when x is 0. So this is going to read cosine of 0 minus cd sine of 0, putting zeros in here and here. Now, the cosine of 0 is 1, and the sine of 0 is 0. So basically, this equation is going to simplify to 0 equals a times b. Now, for reasons that I'll discuss a little later here, the b can't be 0. I mean, if this were a 0 here, this would read y equals just 0 because the sine of 0 is 0. And this over here on the right, see how the d is basically in the same spot as b? This thing can't be a 0 either. So anyway, the b can't be 0, but the a can. And if the a is 0, what happens is if I apply this to our general solution here, I get a solution that's a bit more specific. C cosine dx. So if a is 0, this term is gone. And this is perfectly acceptable. There's nothing wrong with this at all. All right, so we've used one of our initial conditions to simplify the problem down. Next, I can either apply the second condition or I can sub into the equation here. I'm going to go ahead and sub into the equation next. So in order to do that, we're going to need y double prime. All right, so y prime is minus cd sine of dx. Right, we already had that part right here. Y double prime, right, and what we have to do is differentiate this again, is going to be minus cd cosine of dx, because the derivative of sine is cosine, but you have to chain rule, and that brings another d out, which, whoops, I forgot. Right, that's minus cd squared cosine of dx, right? And now what we're going to do is we're going to sub this here and this here. And I'm going to go ahead and rewrite that equation. So if we make those substitutions, this is now going to read minus cd squared cosine dx plus 3 times y, which I'm getting from right here, c cosine dx equals 0. go ahead and make myself a little more room here. Okay. All right, let's see, algebra-wise, the cosine dx can be factored, and so can the c. So this is going to read c cosine dx. Then we're going to be left with minus d squared. And over here, we're going to be left with plus 3 equals 0. And for the same reasons as previous, this cannot be allowed to be 0. Or we wouldn't have a solution left. Same thing with this. So the only thing left is that d equals plus or minus root 3. Now, as far as which one, you can choose one. And it doesn't matter which one you choose, because when I write the solution out, y equals c cosine of root 3x, root 3 times x, the minus sign doesn't matter. Cosine of minus root 3x and cosine of root 3x are exactly the same because the cosine is an even function. So I'm going to go ahead and just take the positive root 3 times x. All right, very last thing here is to apply this last condition here. So we've applied this condition, we've subbed into the equation. This is the last thing that we need to do. Y of 0 is equal to negative 2. So let's see, if x is 0, y has to be negative 2. And let's see, cosine of 0. And the cosine of 0 is 1. So our constant c is negative 2. So putting this together now, our final solution of this thing is y equals minus 2 times the cosine of root 3x. Done. So solving second order differential equations. If you see a plus here, you start with the general solution that looks like this. This is sometimes called the harmonic solution. If you have initial conditions, particularly a 0, apply it first. A lot of times one of these halves will go away. If you don't have initial conditions, what you can do is just sub one of these in to get this value b here. And the value of b and d always work out to be exactly the same. So you only have to plug one of these in to get b and d. And if you don't believe it, just sub both of them in. Sub this one in first, solve for b. Sub this one in second, solve for d. And you can do that because, remember, these are individual solutions. Like this is like a y1 and a y2. Once you find d, well, the b and the d, you're basically done unless you have initial conditions, right? You would then apply the initial conditions to find a and c. So anyway, big things here. You're always subbing in, and then you're always applying conditions if you have them. And that's really it. That's about all there is to this stuff. So hope this video helps demonstrate these concepts. Have a great day.